Good evening, everyone. So, today we will continue with our third talk in the Cosmic Voyages series. And today we have with us Dr. Mayuri S Rao. She is currently an associate professor in the Astronomy and Astrophysics Department at Raman Research Institute, that is RRI, Bangalore. She has completed her PhD from the Research School of Astronomy and Astrophysics of the Australian National University, and she was a postdoc and an affiliate with the physics division of Lawrence Berkeley National Laboratory. Her interests lie majorly in the experimental and observational cosmology. Her current research work focuses on the readout technologies for upcoming and future telescopes at the cosmic microwave background, that is the CMB radiation. Today she will talk about the cosmological experiments, the present day landscape. Over to you, Dr. Mayuri.
Thank you very much. I'd like to thank the organizers for extending this invitation to me. I'm always happy to talk to students. And I'd like to apologize for some miscommunication that happened yesterday. I think the talk was wrongly announced for 24th, but I'm glad people have started showing up for the talk today. So, on that note, I'll get started on this talk. I'll give you the takeaway points first. Um, there are a few major open problems in modern cosmology. Today, I'll focus on two of them. One is called inflation, and the second is something called cosmic dawn and reionization. And hopefully, by the end of this talk today, you will have an understanding of what is this problem of inflation, what is it that we are trying to detect, and how we are going about it, as well as similarly for cosmic dawn reionization, one of the methods that people like myself are trying to detect the signal. You'll have a better appreciation for. I've tried to cover a very wide range of topics, so I'll not go very deep into any of these. Hopefully, I provided some references in each of the slides that you can look up, or we can have a detailed discussion towards the end of the talk or during Q&A. But you can feel free to interrupt me with any questions. So let's get started. Before I get into things, many of you are, of course, maybe familiar with astronomy, given that this is celestic. But when I say cosmology, it is the study of the universe as a whole. We're not looking at a specific star or galaxy, planet, but we are trying to understand the universe as one unit. What are its properties? What is its composition? How did it evolve? And so on. So, any talk in cosmology, you will see some version of this figure. You can imagine that you are on the rightmost part of this image. And if you go towards the left, you are looking further back in time. Our clock in the standard cosmological model starts ticking at some point we call T0 or singularity, or more popularly called Big Bang. Okay. But without getting into what the Big Bang is, are there many other universes that is currently beyond the realm of standard cosmology? But let's say that our clock starts ticking at this T0, then it is hypothesized that there is a sudden rapid exponential expansion of the universe itself when it is about 10 raised to minus 32 seconds young. And within about 10 raised to minus 25 seconds, within that duration, it is hypothesized again that this universe is expanded over 10 raised to 50 times. That's just a number to keep in mind, but that's not fixed. But these are order of magnitude things. This period we call inflation. We don't understand it very well. So that is one of the problems we will talk about today. But we do know that from when the universe is about 3 minutes after its, let's say, birth in this context, most of the matter that you and I are familiar with, which we call baryonic matter in cosmology, comprises of protons, electrons, and helium nuclei. That is the composition of the universe in terms of baryonic matter. There's also dark matter and dark energy, which I won't get into in this talk specifically. But eventually, the universe is expanding and it is cooling, and we also have radiation that is released in this initial moments of the universe. So the components that we do understand, namely photons or radiation and baryonic matter or protons, electrons, helium nuclei, are very um, are tightly coupled, is what we call it, which means they are tightly interacting, exchanging energy, bouncing off of each other, and so on. This goes on for about 300,000 years. And at that point, the universe has expanded enough and it has cooled down enough for the electrons to get captured by protons and helium nuclei, and the first atoms start forming. This period is called epoch of recombination. The radiation, on the other hand, which was bouncing off of these ions and electrons, etc., no longer does that because there is the interaction cross section has reduced, and finally these photons escape from this plasma. This radiation we receive today in the microwave region of the electromagnetic spectrum primarily, and this is called the cosmic microwave background. And it's a very important tool to study the universe, and it's one of the cornerstones of modern cosmology. So the CMB reaches us and we measure it today. But what's happening to the matter, right? Clearly, if you look around you, you see stars and galaxies, you know the galaxies exist, you see the moon, you're on Earth, but none of this has really formed at that point. At some point, typically around 100 million years, we think, the very first stars started forming, and gradually the radiation from these stars and galaxies re-ionize the neutral hydrogen back to its constituents, proton, electron, and so on. So on cosmological scales, so typically what we say 100 megaparsecs or about 300 million light year scales, which is the basic unit in cosmology for distance, the universe is largely ionized. So today we believe, and we have observations to believe, that we live in a universe that is primarily ionized. Okay, so this period when the first stars and galaxies form is called cosmic dawn, and the period following when they reionize the universe is called epoch of reionization. So these are the three periods that I've introduced, namely inflation, there is CMB and recombination, and then there is cosmic dawn and epoch of reionization. So let's look at the CMB very quickly because it's an important tool we will use. If you take a telescope, or if you are able to see the world with microwave at microwave wavelengths, right? If instead of visible light that we are able to see, let's say you have put on some fancy goggles and you can see the sky. Every direction you see will look something like this. It will be a glow with a uniform temperature, because in radio astronomy and sometimes in cosmology we talk in units of temperature, and this will have a value of about 3 Kelvin, okay, which is really really cold. 0 Kelvin is absolute zero, right? So this is 3 Kelvin, okay. But let's say you make even finer, even more precise measurements, and you've corrected for everything that comes in between. You've corrected for all what we call foregrounds, and you're able to make precise measurement at every direction to 1 part in 100,000. You will see tiny fluctuations in the CMB temperature. So it's not exactly 3 Kelvin. It's a little cooler in some spots, a little hotter in some spots. And when we make a map like this of the CMB, we convert this spatial map into its Fourier transform, and we take its square. So we take a power spectrum uh, of this image. We get a curve, and I'll show you that in some time. And this curve matches our cosmological model extremely well. Rather, we are able to work out cosmological parameters like baryon density, dark matter, cosmological constant, few other things like the what we call scalar spectral index. So these are all parameters of modern cosmology, and we're able to work out the details of our universe, its constituents, and its history based on this power spectrum of the CMB. But this is just the temperature, okay? You remember that CMB is ultimately light, and light can also have polarization, and that is what we look at soon. So with this context, let's look at what is this inflation business, right? So until somewhat, I guess in the studies of cosmology until a few decades ago, um, we had a good model of the universe up till this point of the formation of the first atoms. Okay, so we understand from there on everything is clear, but that leaves behind a lot of questions about why is our universe so uniform? So why is this fluctuation so tiny? Okay, and there are other problems in cosmology that we call as generally called as fine tuning problem. It's almost as if the initial conditions from which the universe evolved, is perfectly tuned to have a universe that has the right properties as we are seeing it now in the model. Okay. There is something called as a flatness problem, which means there is a certain density with which the universe is either what we say in general relativity, either open or closed or flat. Our universe is very 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 flat, but it need not be. It could have been open or closed. It could have a concave or convex curvature, but it is flat. Okay. Again, our universe is so homogeneous. Why is it so homogeneous? There is no reason it should be, right? And to invoke this, to solve this problem, this theory called inflation was invoked, where you take the early universe and you expand it suddenly, like I said, and we are looking at only a slice of this expanded universe. So if you take a small ball, for example, so clearly it is spherical, it has some regions that may be one color and another region that may be another color. But let's say you expand it quickly or suddenly or make it a large ball, and you are at the surface of, or you're looking at the surface of the large ball. If this ball is large enough, that spherical surface will start looking flat, if that makes sense, if you can visualize that. Similarly, if 2 points on the ball were initially in contact, okay, and hence they could exchange information, they could exchange energy, so they were somewhat homogeneous, and then they move away from each other quickly, they will still retain that memory. Okay, so this is a very crude way to kind of make this analogy. So inflation does this, but it's not as simple as this, because we don't really know what caused inflation, whether it was even really did happen, or we have to modify gravity to explain these problems. Okay, but one of the hypotheses is that when the universe is really young, it's also really hot. Okay, so the temperatures could have been so high that you are operating in the regime of the grand unified theory. So 10 raised to 27 Kelvin, when the electroweak and the strong force are united. And when it cools just below this point, there is a transition and these forces separate, and this releases energy. Okay, and that energy can cause inflation, is a hypothesis. Okay, so I put some energy scales here on this slide. Okay, this is some 10 raised to 14 GeV scales. And for comparison, the highest collision energy in the LHC is 13.6 TeV. Okay, so these we are able to probe um, energy and temperature scales that we are not and we cannot achieve in the lab. So cosmology directly also ties into particle physics in this context. So I've put a link here for a reference if you want to go into some more uh, um, understanding of inflation. This is by no means a very comprehensive reference, but it has some nice analogies and so on. Okay, so this is what inflation is. That's the problem. We don't understand inflation, but there are experiments underway to try to detect the signature of inflation and hence to understand what model of inflation is correct. So to do that, people again study the cosmic microwave background. Before we discuss that this cosmic microwave background is light, and light has properties. It can have intensity, it can have polarization, right? And it can have direction of from which it is coming. We've already looked at direction from which it is coming and temperature in some sense. By looking at different directions of the sky, you have different values of the CMB, and they're called CMB anisotropy, but that's in temperature. But you can also look at the polarization of the CMB. So specifically to look for inflation, we have a prediction of what we should see if we look for a certain pattern in the polarization of the CMB at degree angular scales. Okay, all of this will make sense when I show you the next slide with some plots. But just keep in mind that at the scales or at scales on the sky of 1 degree in size, we are looking for patterns. Okay, and if that pattern exists, then that is going to tell us something about inflation. For context, when you look at the sky and you look at a full moon, the size of the full moon is half a degree. So you double it, that is 1 degree. Okay, that is an important scale in CMB and cosmology, because that is the scale of the what we say horizon, at this process of recombination. Okay, recombination we say ends at a surface of last scattering. I know I'm throwing a lot of terms here, but I wanted to give you a quick overview so you can go look up some details. But just for all purposes, take my word that we are trying to look for a pattern in the sky at microwave frequencies, very, very faint in amplitude, at about 1 degree scales. So the polarization of the CMB itself can come from multiple things. One is initially the matter and the radiation is, like I said, tightly coupled. So where the photons go, the electrons and protons go, and vice versa. So if there are small potential wells because seeded by some quantum fluctuations, so there are some gravitational potential wells, and matter goes there, it'll drag photons with it. Okay, so there are some regions that are hotter and colder because there are more photons, less photons, and so on. Okay, and this is not necessarily uh, this on average is a symmetric process. Okay, so this introduces something called as an E mode polarization, and I'll show you a picture of what that could look like. But beyond this, there are also some asymmetric perturbations introduced in the CMB because of gravitational waves. So if inflation perturbed this entire space-time metric, there was a large violent energy release, right? That kind of flaps your entire universe, and that gravitational wave should also create some pattern in the CMB polarization, and that we call as B mode. So all of this is the what we're trying to look for. Now I'll show you what I've been talking about in terms of images. I highly, highly recommend the website of Professor Wayne Hugh from University of Chicago. I put a link down below here, and that directly takes you to the animation of this polarization business. But all of his tutorials and papers are excellent, so please look through. So this is what I mean by E and B mode polarization. So on top you can see that there are patterns in both, but intuitively you can make out that one is somewhat divergent and the one below has a curl. Okay, uh, and the one that is on top can come either from inflation or from these what we say density perturbations, basically matter and radiation being coupled. But the one below, which is the B mode polarization, especially at 1 degree angular scale, that is said to be a smoking gun of inflation. So if anybody detects this, that means they have detected inflation if they've done their analysis right. And this is the signal most CMB experiments today are going after. Okay, to date, it has never been detected with any confidence. There have been other detections which are not from the inflation part of which are not attributed to inflation. They come from secondary interactions of photons with galaxies that come between us and the surface of last scattering. But E mode and B mode polarization look like this, and the takeaway is that we have not yet detected this B mode polarization signal, but we are trying very hard. Okay, so
Ma'am,
yeah.
yeah, just a small doubt over here. That
Mhm.
you mentioned about we are looking at only the 1 degree of the sky. So, like, are we going to scale it up to a larger value to get these kind of features, or is it like will constrain to that part itself?
Right. So most CMB telescopes these days, they operate such that they probe a large range of scales. So you should there's a difference between looking at 1 degree of the sky like field of view versus making a map, full map of the sky and looking at how much power is there at all scales. Okay. So to explain better, uh, let's look at this map. It is an all sky map of the sky. Okay, it's been made from space, so it covers the entire 360-degree 2 pi, so 4 pi steradians. You will use this map. Okay, and you will see that on the there is, I don't know if you can see my cursor, can you?
Yes, ma'am.
Okay, great. So there are these really tiny, tiny, tiny dots, but there are many such tiny dots. Okay, assume that each tiny dot is, let's say, a degree. Okay, so you see the amount of power in each of these tiny dots seems to be high. But if I take a big patch, if I take a big patch like this, okay, and how many big patches can I break this up image into? There's one big patch here, one big patch here, then another here. So there is lesser power at this patch. Okay, So when I say 1 degree, I'm not looking at only 1 square degree of the sky. I'm looking at a large part of the sky and seeing how much power there is in each scale of the sky. So within it's like a histogram in a very crude sense. You have a large data set and you're saying this much power sits in 1 degree, this much power sits in 10 degree, this much power sits in one arc second, and so on. So that is what you do with these studies. So I'll take you to that image. So this is the kind of plot you will make from that map that I showed you. Okay. Rather specifically, you will make this plot. Okay. Um, this here, okay, this value 200, okay, corresponds to about half a degree or 2 degrees. Okay. The larger you go in this L, the smaller the scales, the smaller the uh, angular scale. The more towards the left you go, the smaller the number, the larger the scale. Okay. Ultimately, if you go to the value 1 here, okay, you can't do any better. You'll have very large error bars because you have only one universe and you can get only one image of this one universe. You can't have multiple samples of this universe as a whole. And that is called cosmic variance. You're limited by the fact that you have only one universe you can study. Okay, so this is like going here, it's like going to 4 pi steradians. And you can't get many data points in that. You have one data point. Did I answer your question?
Yeah, sure.
Yeah. So yeah, so to kind of repeat what I said, telescopes measure power across the sky. There is a resolution to this image, there is a size to the image, but the plot that you make, you look at the scales, like you take a Fourier transform of the image and this is the plot, this is the square of the Fourier transform. Okay, and if I do that for the image I showed you, you'll get something like this. And the dashed the data is the dashed points are the data, and the curve here that's going through that so nicely is the cosmological model with certain parameters. And it fits really well, you can see till almost this point. So this is temperature. And if I look at the same type of power spectrum for the E mode and B mode, I will get something like this. So it is much smaller in amplitude, about 100 times smaller. And for B, you have B mode that can come from galaxies, which you see at higher, different or smaller scales, which is here. But what we are interested in to understand inflation is this dashed line at the bottom, which is so much weaker. It's like a billion times smaller than the CMB itself. And this has never been detected. And this is what telescopes are trying to detect now. Okay. And I'm zooming in into that bottom part now. And these are all the experiments that I've been trying here. So this dashed line, again, no data points there with any confidence that can say anything. This black line, only now people are starting to make measurements of. Uh, let's not worry about this too much right now because this is not directly related to the inflation problem. But this is a significant achievement to the very fact that we've been able to measure this black line that comes from gravitational lensing of the CMB from clusters of galaxies that lie between us and the surface of last scattering. But to make any measurement about the CMB, we have to get points here. And that is the name of the game. That's what people are trying now. So this is the current constraints we have on inflationary models. This is the current best constraint that I'm aware of. Maybe there's something very recent, I don't know. But we talk about this a number called R. So let's look at what this R is, okay? So I told you that this E mode comes from something called this is called a scalar perturbation or the density perturbation. And the gravitational waves give rise to something called as tensor perturbation. Okay, we know what are tensors and scalars. So if you take the ratio of the two, so if you take the ratio of the power spectrum of this B mode and the E mode, that is called R. Okay, that is quantified by R. So different models of inflation have different predictions of R. Similarly, there is something called as the scalar spectral index, which is the slope of this power spectrum of the density fluctuations. Okay, I'm getting technical here, I won't get into it, but let's just say that this R and NS are the two kind of key parameters that help you identify the model of inflation. So we have been able to constrain some value of R, and this is quite small, so 0.036 at some confidence. But we have not yet made a detection, and that is what experiments are trying to do now. So what does it take to make this detection? So here, I wanted to include a slide, but I missed doing that. So I'm just going to direct you to go and look up CMB telescope and to get an idea of what a CMB telescope looks like. CMB telescopes, interestingly, operate at the border of the wave and the photon nature of light. Okay, because you're operating at the peak point of the black body spectrum, you can treat this radiation as photons when convenient. So you can have optics and detectors and mirrors and lenses, and as a wave, so you can also have antennas and so on. And these are extremely complex, large instruments that get deployed in space, and now, of course, several are coming up on the ground. And right now, we have come to a regime where if you want more sensitivity to get more, to make better maps of the CMB, you need to increase the number of these detectors. Okay. And you have to increase the number of the frequencies at which you look at the CMB. It's not good enough if you look only at the center frequency where the CMB peaks about 150 gigahertz. You also look at 200 gigahertz and 20 gigahertz, and all of this helps you separate the contaminants from your data. You have to go to a site that has very little atmosphere, so you go to very high elevation, very dry sites like Chile or South Pole, or better, even space. You have a lot of algorithms that go into cleaning up the data, making the maps, and so on. So this is the current name of the game. Our current best intensity map of the CMB comes from a telescope called Planck, and this map that I showed you is from Planck. Okay, this is from Planck data. This extremely high resolution map with an accuracy of about, you've gone down to 1 part in 100,000, that is the level at which you've been able to make out details, was made with only about 60 detectors across 6 frequencies. Okay, and it operated from space, so there are advantages there. That is called as a stage 2 experiment. Now we are in the regime of what we call stage 3 experiments, where we have tens of thousands of detectors in each telescope. And I've listed some of these here, and you can go look it up. And all of these operate typically using superconducting detectors. So you have a photon that comes and falls on a superconductor at its transition temperature, and the, the photon heats up this detector, and that heat results in a change in the resistance, and you are able to detect this change in resistance and record it as a voltage. I've simplified this a lot, but it's extremely cutting edge technology in superconducting research, and people are working with new materials. And this is those of you who are in physics, who are interested in, say, superconductors, there's a direct connection to these um, detectors in this in cosmology. So most CMB telescopes use superconducting detectors, and there's extremely complex circuitry that makes sure you're able to bring the signal from the detector level to a computer. Okay, and you need to pack tens of thousands of detectors in a small area, which is the focal plane of the telescope, and still not let that area get hot, because there's a lot of wiring and electronics that it takes to communicate with this. So there is a strong cutting edge technology angle here. For those who are interested, you should look into these things. The next stage CMB goes to is called as stage 4, which is already proposed, and that will have 100,000 detectors, so even higher order of magnitude, and it will operate from 2 sites, both in Chile and South Pole. Okay, so I'm part of this experiment called Simon's Observatory, and I won't give you all the statistics, you can go look it up, but Simon's Observatory will have about 60,000 transition edge sensing bolometers at their focal planes, operating over 6 frequency bands, and it will push the sensitivity level of this R measurement even further below what our current best estimate is. So here's a nice pretty picture that I like of the site at which Simon's observatory will operate. So physics students who are interested in cosmology, if you get into, especially if you get into the experimental side, you will get to build telescopes and experiments and deploy them at really nice, interesting location if that interests you. Okay. So I showed you a plot earlier from Planck and bicep Keck data. Here is the current predicted estimate of what Simon's observatory will do. So the gray stuff is what our current limits are, and with Simon's observatory, we can, if it works really well, right, you will be able to get to this area here. Okay. Within this dashed line is the goal that we want to work, but we'll take the shaded region that's called the baseline, and this is set to operate in 2020s. And for CMB S4, which is even more futuristic, we are pushing the limits even further down, and we'll start probing regimes that are theoretically very sound and probably the most likely candidates for inflation. We may make a very good detection. So that is about how CMB experiments are operating now, the kinds of work it takes to build, and what it takes to look at inflation in a very quick overview. Um, Very quickly, I just want to say, since some of you may be interested in doing cosmology, especially experimental, this part of cosmology, especially CMB telescopes and this inflation and B mode business, it is now at the scales where the particle physics community is. So there are hundreds, if not thousands, of people working on one experiment across the world. So here is a map showing the CMB membership across the world, and it involves a team of highly specialized scientists, students, postdocs, vendors, um, contractors, and it's imagine like putting up an LHC but for CMB. That is the scale to which this field has progressed, and there is a place for everyone. So if you are interested in cosmology, and you are not able to make the jump to that field right away, you can be a material scientist and get into this. You can be a computer engineer and get into this. There is a place for everyone, so you should keep an eye out for positions that may interest you in such experiments. I'll take a pause here before I shift to the next completely different topic. Are there any questions at this point?
I have one question.
Yeah.
Like, are there any particular reason why we are using superconductors in stage three?
Yes. So uh, superconductors have been used more or less all along for CMB, other than when it was originally detected. The reason being that the CMB is really cold. Okay. So it is 3 Kelvin already. Okay. So if you just take an antenna at 150 gigahertz, connect some receiver to it and put it up at the sky, right? First of all, you'll have to cool your electronics. If not, you will be looking at your own receiver. You won't look at the sky. You will be receiver noise dominated, is what we say. So let's say you cool that. But then you need to make sure that you are limited by the photon noise. So the CMB should be able to make a difference in your signal. It should make a blip. If not, it'll be buried within everything else. So superconductors are among the more useful ways to get to the sensitivity levels that you need. So if you do everything right, if you cool your optics, so you can imagine there's an entire large telescope with a um, with a tube, with a telescope tube and lens, and the walls of the tube, everything is cooled in these telescopes. Okay. And you gradually cool them from room temperature 300 Kelvin all the way to 100 millikelvin, and there your detectors are sitting nice and cold. So any photon that makes its way to that detector is able to make the superconductor transition from being superconductive to normal. And that transition is something that you can detect as a current. So it's mostly for sensitivity reasons. To be able to actually see something that is so cold at such a low level, you have to use something equally cold.
Okay, so another follow-up question to this, like in this particular case, like if the signal is still buried in between the noise,
Mhm.
and so how can, like, let's say if it's an instrumental noise, is there any way to like filter it out?
Um, so it depends on what kind of noise. So noise can have different types of spectrum, right? You've heard of white noise, pink noise,
Yes.
red noise, and so on. So every telescope, when it is being designed, you pay attention to the details to every single element of the telescope to make sure that in the band where you're operating your telescope, you are not noise dominated. Once your instrument noise dominated, you can't get out of there. If you are in the regime where you are getting photons from the CMB, there is also instrument noise, but the instrument noise averages down with you with integration time. Okay, that is basically it's like white noise. Then you're okay. But if you are getting photons where even on averaging your instrument noise is still has a slope or it's still dominant, you can't separate. So you do all the techniques, you do averaging, you do filtering, all that, but your instrument noise has to average down, and you have to design your instrument where this happens. So
Okay.
in one frame, in one recording of the data, you will suddenly not see the CMB, you will not do it. There's a lot of effort that goes into it, but your instrument should have been designed such that this noise reduces after several frames get averaged, for example.
Okay. Yeah. So you mentioned like different methods of like improving the data,
Mhm.
and but in stage 3 and stage 4, both of them we are seeing that you are just increasing the number of detectors. So are we going towards some other methods as well that you mentioned before?
Yeah, so that's actually a very good question, because right now the way we think of course you have to pay attention to everything, you have to make sure you have the correct type of FPGAs and computers and algorithms, all that is still happening. But in terms of instrument, the current fundamental limitation uh, in the CMB field is that we are right now what is called photon noise dominated. So, which simply put, that just says the more photons we get, the better. Okay. The best way to get more photons is to have a larger focal plane and to have more detectors. And that is why this jump in the number of detectors.
Okay. Thank you.
Yeah.
We have one question from the chat. Okay, okay. Yeah, Bijas, you can go ahead, then I will tell the question.
Yeah. So, one of the main problems for detecting the B modes I have heard is the emission from the dust grains.
Yes.
There have been independent efforts to quantify the contribution from the foreground dust clouds along different line of sights where the CMB radiation intensity is high.
Yes.
But I have heard, but is it part of Siemens Observatory also? Like, do they have that also has an important aim for that, like removing the foreground contribution from the dust clouds?
Yes. So does contaminate our signal. It is an important but not the only foreground to CMB and CMB polarization. Dust can result in polarization, which is why, in addition to having robust foreground separation models and algorithms and so on, it's important for all these telescopes to have multiple frequency channels like Simon's Observatory has. So it has 6 bands you see here. And why that's important is, let's say CMB is at at the heart of it, you can treat the CMB as a black body, and the black body has a certain spectrum shape. So which means at different frequencies you expect it to have different amount of power. Dust, on the other hand, has a different frequency spectrum. It can be a gray body, and that has a different uh, functional form. So, by having data samples at different frequencies and you fit to your data for both dust and CMB, you'll be able to separate them. This is not as easy as it sounds, but it is important to do this at multiple frequency, which is something that is happening now. There was a result that had caused some stir but turned out to be dust, etc. And one of the issues there was the number of channels and the analysis with that. So yes, it is. This is part of Simon's observatory, and it will be a part of any CMB experiment, especially relating to B modes.
Okay. So for quantifying the contribution from dust, you'll be using which band polarization data in Siemens Observatory? Uh,
We use all bands, but dust is dominant at higher frequencies. So dust emits more at infrared. So more at 225 and 280 gigahertz, whereas CMB is dominant at 145 gigahertz. That will be your CMB channel. 27, 39, and 93 will be more of your synchrotron emission from our own galaxy, that channel. 225 and 280 will be used more for dust, but for the analysis, everything will be fit jointly.
okay, thanks.
So there's one question in the chat box.
Mhm.
So Nandini asks that did we have any specific system development for cancellation of while white main cancellation of noise while main detection, external or inbuilt?
Um, I don't quite understand the
Okay,
question.
okay. She asked that did we have any specific system development for cancellation of noise while main detection, external or inbuilt?
Okay. I'll answer this in a different way, the way I understand the question. You'll never have any now noise cancellation system, because at the end of the day, remember, even the signal that you are observing is electronically shows up like noise. It's just that this is useful noise and everything else is useless noise. Okay. But you have something called calibration, and calibration is to make sure that you are able to separate some instrument components from the sky components, and CMB components from other you are able to make sense of what is instrument noise and what is useful noise. Okay. And yes, for that we have various techniques, and people again specialize in that, and they have come up with very fancy interesting techniques like magnetically levitating, spinning birefringent materials. You can look up a cryogenic half wave plate. Okay, CHWP, Simon's observatory. So these are, and they have several checks and balances in place at each stage to calibrate the response of the instrument and hence its noise contribution, and help use that to separate that from the sky or the CMB contribution. But you never cancel. You will understand the data better to make sure you know this is useful noise and that is bad noise. uh,
Yeah, thank you,
yeah.
ma'am. I think you can go ahead.
Yes, so I'll go over this part a little quickly because it's already been more than an hour. So very quickly, I'll rush through this part. So the next problem that people are looking into, including myself and my colleagues at Raman Research Institute, is this problem of cosmic dawn and epoch of reionization. So this is when the first stars and galaxies form and they emit radiation, and that radiation reionizes the universe to its ionized state. So we are currently living in a ionized universe, and that ionized is at large scales, 100 megaparsec scales. You and I are clearly neutral, right? So this is all cosmological scales. And the problem is that we don't know exactly when the first stars galaxies formed. We don't know what type of radiation they emitted. We don't know how this radiation interacted with the gas and reionized it. So there are a lot of open problems. There are many ways to try to study the to study this period, including the CMB itself, including Lyman alpha emission from stars and galaxies. But today I'll focus on a specific signal, that is the 21 centimeter signal from neutral hydrogen. And even in this, you can make different types of measurements. But we will look at one specific type of measurement called the global or monopole signal. So, what is all this about? So, very quickly, we said that the universe transitions from being neutral hydrogen to ionized. So, as I go from the left to the right of the screen here, when there is neutral hydrogen, it emits neutral hydrogen emits a signal called the 21 centimeter signal, which results from the hyperfine splitting of the 1s shell. So the electron and proton can have aligned or anti-aligned spin. So when the spin changes from aligned to anti-aligned, it comes to a more relaxed state, and it releases a photon of frequency 1420 megahertz corresponding to 21 centimeter in the rest frame in the lab today. But if you go back in time or you cosmologically redshift this signal, it will have longer and longer wavelength or lower and lower frequency. If you look collectively at the universe as a whole and see how much neutral hydrogen there is, okay, so how much 21 centimeter emission is coming towards us, but it is coming towards us with the CMB as a background, okay. So you can imagine that the CMB has a certain temperature. You can quantify this 21 centimeter signal to have a certain temperature, equivalent temperature. You're looking at the difference of the two, okay. Hence the difference can go negative. So you're seeing temperature in Kelvin here, negative Kelvin here, because you're seeing this in absorption from a background radiation. This shape, okay, is one of the models that tells you the evolution of neutral hydrogen as a function of cosmic time or equivalently frequency, okay. um, this type of signal has been predicted. There are several such variations of this signal, but none of them have ever been detected. But if you're able to make a clean and very nice detection of this signal, you will be able to work backwards and say something about the first stars, galaxies, when reionization happened, what type of radiation these galaxies emitted. All the astrophysics is hidden in this signal, and we are trying to find the signal, okay. And we call this global 21 centimeter signal, okay. um, I've already gone over this slide, which tells you what the 21 centimeter signal is and what we're trying to look for. So I'll just move ahead. Like I said, there are many, many variations of the signal. So here is the black one, is the one I showed you before, but the signal could be brighter or dimmer, have these turning points at different frequencies, and each of this corresponds to a different mapping to the astrophysics and cosmology, okay. So if you're able to detect the true signal in this forest, or maybe it's something that I've not even plotted, you can work out the astrophysics and cosmology. So this is the name of the game. This is the signal people are hunting for. And you should realize that this is very, very dim, okay. Um, the signal has an amplitude of, let's say, at the most 100 millikelvin, okay. Our own galaxy over this frequency range can be 1000 Kelvin. So you're trying to detect a needle in a haystack and you don't know what the needle looks like. So it's a very, very tough problem. And this frequency range is 55 to say 40 to 200 megahertz. This is bang in the middle of this is our own FM transmitter frequency range, right? 88 to 108 is where you tune into all your FM stations. And that is a big, big problem for all these experiments. So this slide has become very blurry, sorry about that. But already we have started making some constraints. We have started rejecting some of these models based on some measurements. I'll get into that later. So again, here are some papers. I'm just leaving it on the screen so that you can look it up later for some recent results in this field. But there are two experiments I'll cover quickly. One is called SARAS, which is an experiment from RRI. And SARAS has existed for a long time and it has taken different variations. We've gone with SARAS to Gauribidnur, we've gone with SARAS to Anantpur, to Sharavati, to Ladakh, and we have evolved the design of our antenna to be able to make such a detection. Okay, hence you see very non-standard shapes. So it is not like a traditional radio astronomy telescope, but it's a very funny looking custom designed antenna that we used for these experiments. And again, if you get into this field, you will get to go to places like these, you get to go to Ladakh, and you'll get to see night skies like this. This is a photo taken at Saras deployment in Ladakh. So we were like, the team was camped out here in a tent. There's a truck that's operating the batteries for the telescope sitting somewhere in the field, and this is the night sky that day, of course, integrated over some time. So Saras also has now gone to float on water, and I'll tell you why quickly. But this is the kind of current, potentially the best experiment in the world with the latest results in this field comes from our lab at RRI. And this is an image of what that looks like in operation. Okay. So let's look at what the problems are for such an experiment beyond the fact that it's just hard to do. Okay. You have an antenna that sits on a surface, either water or on the ground. And because it's so custom designed and so sensitive to detect this signal from the sky, it'll also see everything below it. It'll see the rocks and pebbles and waves of water, everything. So it is sensitive to not just the things that come from the sky, but also beneath it. Then you have RFI that comes from mostly FM transmitters. You also have effects of the ionosphere. Okay, all of this is a problem. There are several other problems, but these three specifically are problems that affect ground based instruments. So, to overcome this, several experiments have been proposed to operate such an experiment in space. And the best place to operate such an experiment is the far side of the moon, the side that you never see. Okay. And there have been several simulations and data sets that make us believe that that's where we should be doing these experiments. And several experiments have been proposed, including from our lab at RRI called Pratush. So you can go look some of these up, and I'll be talking about Pratush very quickly and I'll wrap up. So I'll just jump across these. So Pratush stands for probing reionization of the universe using signal from hydrogen. In its full configuration, it will operate from 40 to 200 megahertz. But right now, we are working on the 55 to 110 megahertz, focusing on the cosmic dawn. It will be a lunar orbiter in its final stage, and it will observe the sky from the far side of the moon, where there'll be no ionosphere. It will be in orbit, so there'll be no Earth it's actually sitting on, no soil. So it'll be in free space, and there'll be no RFI. So it solves all the problems. Of course, it's a very complicated experiment to do, but we're happy to say that after completing just over 2 years in the seed funding stage, we've got the go ahead from a technical review committee from ISRO. But now we are working towards going to the project phase. That has not yet happened. So this is what Pratush will look like in a kind of cartoon model. You have an antenna that is sitting on its own dedicated bus or craft. So we are not a payload going with other experiments on a large satellite. We will have our own dedicated mini satellite is what we envision. And that will have all the electronics that will operate Pratush. Uh, and this is what it looks like today. We have a laboratory model that's functional. We have been testing it rigorously in the lab, and we will soon be going out to the field. Okay, and here are some, I don't think this is interesting enough for this talk. So I kind of wanted to jump to the end to say that there is this signal that comes from cosmic dawn reionization. There are several experiments underway trying to look at it from different angles. One such is this global 21 centimeter signal that we're already doing really well with at RRI with Saras. But we are thinking, one step ahead, and we will hopefully be flying around the moon eventually. But right now, our plan is that we will do a phase one Pratush operation in Earth orbit. Okay, we'll be orbiting Earth. We will still see terrestrial RFI that we have to account for, but we will still be above the Earth's ionosphere for the most part, and we'll be operating in free space. So we'll have a higher confidence in our signal measurement. And Saras and Pratush will do a joint measurement in the initial phase, and eventually Pratush will orbit the moon. And this is the way the field is proceeding also. So it's just like us, there are experiments around the world trying to make this first detection. It is a pretty heated race. And if any of you are interested in being part of such experiments, you can write to us. We have a visiting students program at RRI, which is pretty competitive. And you can look at developments in this field across the world and approach people to work on this for your higher studies and so on. So I'll just leave this concluding slide here and I'll close. I think I've taken up enough time.
Thanks a lot, ma'am. We really enjoyed your talk. So if anyone wants to ask any questions, they can now unmute and ask. Okay, if not, then I have one question over here. That okay, so you mentioned about the gravitational macrolensing part. So like that is a way to like detect such signals. But in this case, are there any such method? I mean, does it matter in which? Okay, I will rephrase my question. Like you mentioned about the far side of the moon.
Yes.
So like, why is it like a good site? Like, how do we choose such sites?
Oh, okay. So you can imagine the moon as an attenuator of radio signals. Okay. So the moon is like okay, let's say you have good wi-fi strength in some places of your house, but in some rooms you have poor strength. That's because your radio signal, which is basically wi-fi, it's maybe some 2 gigahertz, 2.5 gigahertz, is not able to permeate through the walls and then get to you. The moon does exactly that for radio frequencies, especially at our frequency range. So all the RFI that is coming from earth towards the moon eventually gets absorbed or scattered off by the moon, and the back of the moon that we don't see is expected to be very radio quiet. Of course, the back of the moon also sees the sun sometimes, so we have to operate when we are not seen by both the sun and earth. Then it is very very radio quiet, so moon is just an attenuator of radio frequency.
Okay, yeah, thanks a lot.
Hi, I have one question regarding the first part of your talk.
Uh-huh.
So you spoke a lot about the power spectrum and how for new experiments are trying to focus on the low multipole ranges.
Yes.
I have a My question is quite theoretical. What do you think are challenges as we move forward, as experiments get a lot more precise? So with precision cosmology, what challenges do theorists face? Because I ask this because I'm starting off something in that side, but I don't exactly understand the field myself.
Okay. um okay, let me put it okay, I think I'll give my take on this. It could vary.
Yeah.
Right now it's a bit of a wild game. Okay, there are some models that have already started getting ruled out and some models that are far far beyond reach. Okay, at some point, hopefully soonish, 2020s if not 2030s, we will start placing bounds, not just upper limit but also upper and lower limit, that will tighten the parameter space within which theorists need to make sure that models make sense. Because remember, the models should not only predict everything that has already been measured correctly, so that it doesn't say that I'm predicting the universe has does something completely different whereas you're measuring already very well. Okay, so you have to make sure that the parameters that your model predicts are within these bounds that have started that have been bounded by experiments in the future, but also that they're able to make clean predictions of what the next generation experiment should see. Put it differently, let's say that this is a bound. Okay, but there's, remember, this bottom bound is not yet constrained. Let's say I constrain it, let's say I constrain it with an experiment here. Okay, I'm in this circle. Your model of whatever cosmological inflation and CMB and everything that the universe should operate within should fall within this, predict everything that has already been measured correctly within this, and make predictions that tightens this sphere. Okay, and that will become the regime of in which theorists will work. Just like when CMB was originally detected, you knew it was going to be 3 Kelvin, sure. You knew it's going to have a power spectrum, but you have to start making the power spectrum prediction to the thousandth multipole. And then you have to you have to tighten your prediction, because soon data will start catching up. And if your prediction is well outside the data error bar, then your model is out. So that's probably where it's going to go once experiments start catching up with the theory.
Okay, great. So, to understand it in a rephrased version of myself, so for example, if I wanted to constrain the scalar spectral index or
Yes.
the R, the ratio, so
Yeah.
I would have to start by making a model that reduces the error bar enough that even experiments would have to go a bit further.
Yeah,
Essentially.
it's not just the error bar and it's not just the R and the NS, but your entire your model of the inflation should fit within the at least the current best data of the lambda CDM measurement in that paradigm, and it should tighten this circle. So let's say the current measurements have been all here, right, in this gray region.
Mm-hmm.
If you say that your R and NS is here, then it doesn't make sense. It's ruled out already because we
Yeah.
do have confidence in our measurement. So your model is going to sit somewhere here, let's say, after Simon's observatory. But where here is your prediction. That is the game, right? And then it should predict not only the R and NS, but what is the running of the NS, for example. And you should make the higher order prediction beyond just the RNLS, right? You will have, is there a tilt? Is there running to the tilt? And if there is, what will this landscape look like?
I'm sorry, could you rephrase the running to the tilt? I didn't catch what you meant there.
Oh, so your tilt is the slope. The slope can have a curvature.
Ah, okay, okay, yeah, all right.
So what is is there a curvature or no? Right now, all of that is like wild territory in terms of models are there, but data is not yet kind of pinning things down
Yeah,
very well.
okay, yeah, got it.
Yeah.
Thank you.
Yeah. So you'll go beyond the, right now we're trying to detect something, but once it's detected, we will try to measure it better. Just as CMB was originally detected accidentally, but it was detected. And then Kobe went up and measured the dipole, and then WMAP went up and measured the anisotropies to a certain L, and then Planck went up. That'll be the trajectory even for the B mode signal.
Yeah, yeah, no, that makes sense. Great.
Okay, so I have like one question, but that is not fully towards the talk that you gave.
Mhm.
So my question is that there has been a recent publication in the monthly notices of Royal Astronomical Society
Mhm.
regarding the JWST data, where some researchers have found out that, I mean, they have claimed
Mhm.
that the age of the universe might be double than what we have expected till now from the redshift they have observed from very distant galaxies. So in now there has been a debate about like whether that is correct or not. So if let's say a hypothetical case that such kind of results come into picture, then how will these experiments get affected for that?
Okay. So I would like to re-emphasize that these are really preliminary, and you're right in that we don't really know if that's quite correct. And at the moment, I think the community is leaning towards I don't think that's correct. But let's say that's the case. Okay, it's not just about higher redshift and double the age. I think the result you may be talking about, I could be wrong, is that we think that at different redshifts there should be a certain distribution of galaxies of a certain size. But if, let's say, you find suddenly that there's this really large galaxy sitting further beyond where it should have been,
Yeah,
okay,
yeah.
that pushes this cosmic dawn and epoch of reionization further beyond. Okay, so in terms of the measurement, right, let's say this is correct. Let's say we have confirmed, but very unlikely that this is the case. Then in the context of, say, global 21 centimeter signal detection, you will have to change the band of your experiment. So what we think is now between 20 to 200 megahertz or 40 to 200 megahertz will now shift even lower in frequency. So instead of looking here, I say 78 megahertz or 70 megahertz for this signal, you will start looking earlier, lower frequency or earlier redshift. So that is the way in which these experiments will try to look for signatures of earlier structure formation. And the same will apply. So even in CMB studies, right, there is a certain model that tells you where these peaks lie and at what scales you should be seeing power. And correspondingly, there are other experiments that look for what we call as baryon acoustic oscillations, that look for these power spectrum of the matter, right? And everything will, it'll have repercussions across cosmology, but I don't foresee that happening uh, because of these results are extremely preliminary.
Yeah. Okay, that makes sense. Yeah. Thank you. Thanks a lot. Are there any other questions?
I have an extremely broad question, which may not be entirely relevant even, but Where does Euclid fit into all of this? I mean, it's a completely different wavelength band, but we're still talking about lensing cosmology. I
Uh,
mean,
yes. So, so first of all, Euclid will be the space-based experiment, so it'll have a different kind of way in which it operates.
yeah,
And I think specifically they'll be trying to understand dark energy and dark matter. I don't quite categorize it as a CMB experiment. It's not. Okay.
yeah,
But it will make, for example, we have galaxy surveys. Okay. So our best galaxy surveys come from something called the Sloan Digital Sky Survey, SDSS, and now there are many, many more. There's something called Wiggle-Z and DESI and so on. So what they do is they try to trace this cosmic timeline by making spectroscopic measurements of galaxies, which is basically to say that, like you're trying to make a CMB power spectrum here, you'll try to make a matter power spectrum
yeah,
by tracing these baryon acoustic oscillations, and tells you, which will tell you as a function of redshift, the galaxy distribution. And that, of course, is an important way to study structure evolution, and that is directly related to how much dark matter there is and how much dark energy there is,
mhm,
and how that is going to affect the evolution of baryonic matter structure formation, right? And
yeah,
yeah, that is the general broad stroke how Euclid is different. But yeah, they're all ultimately trying to address the same problem of composition of the universe and history of the universe as a function of redshift.
yeah. Okay, that was a broad question anyway. Thanks a lot.
Yeah.
If there are no more questions, we can wrap up. Okay, yeah. Thanks a lot, Dr. Mayuri, and we really enjoyed your talk and it was really, really informational. Yeah.
Thank you. Thanks, everyone.